Well, hello friends. Today we are going to play with the performance analysis tools that we've been building. So we're going to take the profiler and profile some stuff and then see if we can find something interesting. But first thing I got to do is show you where the profile viewer is at. So let's get a profile of starting the browser and we close it again. And then we bring up profile viewer. And I can show you now that this instruction view down here is really getting kind of interesting because I've added this sort of heat coloring of which instructions we spend the most time in, and I've also added symbolication. So now when you have like a jump here, for example, you can see not only the address, but the actual name of where it's jumping to. So in this case, it's jumping inside of the function. But of course, you can also see external jumps. Like for instance here, it's a call to inline linked list inside malloc. So pretty interesting stuff. And I also fixed a bunch of issues with profiling in the kernel because it was not showing us the innermost frame. So everything was aggregated at the second to innermost frame, which made profiles kind of weird. But now we actually see the stack the way that it is. So if we flip this around and we just look at the browser starting, we can actually see, if we look, like follow it all the way down, we can see the innermost frame everywhere. Previously we would get stuck here and not see this one. Anyway, pretty cool. So I figured today we could profile some things and then see what we learn and what we can fix. So the first thing I would like to do is, of course, to profile that JavaScript ray tracer thing that we worked on. So I'm just gonna bring that up right away. So here we go. All right, 5.3 seconds, not the strongest, but you'll notice that we ran and it came out the right side up. Previously it was upside down, so this is because earlier today I implemented some basic affine transforms for 2D graphics in the browser, so that makes the canvas rotation come out right. Anyway, let's look at this profile. So very, very intense looking profile. We'll just select this part here and flip it upside down. And this, now we can definitely see that we have a different profile than last time, because last time we couldn't see the innermost parts. So we had like malloc and free, and like the hash map was at the top of the inverted tree. But now that we see the innermost frame, we can see that actually the syscall entry point in the kernel is the single heaviest location, followed by the gettid, which is extremely busy, as you can see here. And it's being called by malloc and free and various other places. And gettid is just get the thread ID. Basically, it's like getpid, but for your thread ID. And all the threads in a process, they all, like if they all say getpid, they get the same number. But when they say gettid, then they all get a unique number. That's like their thread identifier. And we use that in the user space locks to figure out if when it comes to a recursive lock, we use it to figure out, am I the one who's holding this lock? If so, I can like increase the level of recursion on the lock. And there's probably better ways to implement lock recursion, but currently we use gettid for that, and we're doing a lot of it because we lock. We take a lock on every malloc and on every free, as you can see here, and it's just totally chewing up the profile. So we used to cache getTid so that you would never make the syscall more than once, but then so we used to do this thread tid cache, something like this, and then like if tid cache is -1, then tid cache is call the kernel. So this means that you don't have to do the syscall anymore, because the syscall here is what's heavy. You can see that we make a syscall and then the ret is the heavy instruction here, because we can sort of catch this process while it's waiting to return from the interrupt. But we had to get rid of the caching for some reason. It was because when we fork, then the did cache would stay. Right, so when we fork, then we would clone all the memory, and now you have a new thread ID, but we still have the old thread ID in cache. So it would become stale on fork. That was the problem, right? So I would like to cache this though, so we don't have to go through the kernel. So what if we would put it into some memory that would get cleared on fork? So I know that the BSDs have a way to say that, like, when you fork this process, then this piece of memory should be cleared. It's called like minherit, or I think. I have to look that up. No, I wanted minherit. Yes. So the inheritance of pages, right? So it's sort of like an madvice API, but instead of madvice, you have minherit, and then you can say like what's going to happen to a region of memory on fork. So I think this is a very useful API, and it's not some POSIX thing. It's might be a OpenBSD specific. I don't know. FreeBSD looks like they have it. OpenBSD. Okay, so it's an OpenBSD thing. Well, it wouldn't be the first thing that we borrow from OpenBSD, so I think we should get this API. And then what we'll be able to do is we can put this thing here in like thread info cache, something like this. And then we'll say that we have a thread specific thread info cache. I guess thread info cache, whatever, and then we will check. If we don't have this, then we will allocate it. So thread info cache and map null putter one page, or I guess if we're going to be good boys, we can even do page roundup of the size of thread info cache. And oh wait, page roundup is not even a thing. Maybe it's a kernel only thing. Anyway, it's not going to be bigger than a page, so whatever. So we'll say this, and then it's, wait, what comes next? Is it prot? I should remember this. Why isn't it autocompleting? prot. I always mix up if prot or map comes first. So prot read and prot write and map anonymous. Okay, and then we'll just assert that this is not map failed, because then we will have failed quite badly. And then we will say minherit thread info cache page size, and what was the name of it? It was, I wanted the OpenBSD one. Map inherit 0. New pages will be 0 in the child process. So this is what we want. And I guess we can say if this fails, we will do something like this: map inherit 0. Assert not reached. All right. So now we know that if we fork, everything in this page here will become, everything in the struct will become zeros again. So then what we can do is, if the thread info cache tid is 0, then we just have to populate it. So we'll call the kernel get tid, and then we can just return it. Okay, something like that. Now, of course, we don't have the syscall, so we have to implement it, but I think this idea is pretty decent. Maybe there's some obviously better idea, but this feels reasonable at the moment. Let me know if you think of a better solution for this. So we'll add a syscall for this to the list of syscalls. It's been a while since we added syscalls. Minherit. Thank you, OpenBSD, for inventing nice things. So I guess we'll put it next to madvice. And what do they call that? Inherit or what? Yeah, inherit. That's pretty okay. So let's put this in the stdio pledge, and let's see, address, size, region from range. So we'll look up this range that we were just given here, range, virtual address, address, size. Then if we don't find this region, we'll just say, dude, I can't help you with that. Ian Val. I'm sorry. I think that's what we normally do anyway. Just that we normally write it this way, apparently. It's been a while since I was hacking on the kernel, I can tell. So let's see. I guess what we want to do now is just say region set inherit, and then return 0. So it's pretty straightforward. Maybe we should simplify this actually a little bit. So it would say if inherit and map, I already forgot what it was, map inherit 0. So if this one is set, then we'll say set inherit mode 0, something like that. Yeah, and then we can actually fail for unknown things. Okay, so let's go and add this to mman next to our mdevice flags here. I guess this will be the very first one, so 1. And oh, we should also add it to the Unix types. So madv. Okay. And then the VM region class is going to need inherit mode. So we'll just add that enum class, or let's say inherit mode. 0 on fork, maybe. Yeah, that's pretty good, because I want something that's very expressive, so we could even call it like fork action 0. No, this is better. 0 on fork. Zeroed fork. Zeroed. Yeah, that sounds nice. Zeroed on fork. Okay. And then let's also add that thing that we called set inherit mode. Inherit, and this will be, actually you're only going to have one mode, right? Yes, they're exclusive, so it's not a mask, it's like a single one. You only get one. We should set this to kernel mode. We immediately got into kernel hacking here instead of profiling, but it's good. This will be very helpful, I think. So we'll say inherit mode, and this can be an enum class. What's the default mode anyway? Map pages are shared. Map inherit copy. Curious. Okay, so I guess the default behavior is different for different regions, but I think we're gonna have something here called like default, and this will be the default mode where we just defer to the default policy, and then we can look into the other modes here later on. Because right now I'm only interested in zeroing the memory. So we'll put a little enum for this guy. So inherit mode. Inherit mode. Can we give him a bit field size, like 2? How big is this thing? 48 bytes. What if I don't do that? Oof, grows so much. Alright, so we'll give it 3 bits. We can live with that. Alright, so that's looking pretty cool. Now, this shouldn't be and, it should be equal. And we can do it this way instead. Case. Return 0. Nice. All right. And then when we do a fork, then what we do when we fork is that we create a new process, the very first thing we do, and then we iterate through all of the memory regions of the current process, and then we clone each one and add that to the address space of the child. So here we call it region clone for each of our regions, and region clone is where cal mappings are created and things like that, and it's sort of where we decide what to do with a region, and it's based on the flags of that region. So I think here basically if inherit mode is inherit mode 0 down fork, then I guess this should only be available for anonymous pages, anonymous M mappings. So we'll say assert that the VM object is anonymous, because I don't know how this would work for files. That sounds weird. And I think we'll enforce that at the mmap level. Or not at mmap, at minherit. We'll say that we'll only let you do this stuff for anonymous mmaps. So if it's not an mmap region, you can screw off right away, because you're not supposed to touch non-mmap regions. And if region VM object is anonymous, then you can't do this with a non-anonymous region. I wonder if they allow this for anything. Not all implementations will guarantee that the inheritance characteristics can be set on a page basis. Yeah, we're not caring about that. Yeah, I'm primarily interested in this one right now. So we're skipping thinking about all the other stuff, and we're only implementing this particular behavior. So now that's the inherit mode, and wait, where do I want to go? To set? No, I want to go to clone. Clone, right? So it is anonymous, and what we normally do is here we just fall through. Unless it's shared memory, then we just fall through down here, and this is where cal or copy on write is implemented. For memory regions. So basically, for cal region, we just create a new region that is backed by the same underlying VM object. That's how cal works. So it's like originally a VM object that has all the same physical pages, but they are write protected, and then the kernel intercepts writes and turns them into copies. Anyway, in our case, we just want to make a new region and return it, because this is all about cloning this region that you're calling it on. So we'll say like zeroed region is region. Create a user accessible region with the same range, but we want to make a new anonymous VM object. Create with size. And I guess the size of this region, and the offset in the VM object is 0, and the name is the name that we have, and the access bits are the access bits, and cacheable we don't care. So then we just have to make it look like an mmap region. So actually we can assert that it is an mmapped region that we're cloning. And zeroed. If it's shared, I don't like the idea of shared memory being 0 down fork. That sounds really stupid and bug prone, so let's just say that we don't tolerate shared either. And we will propagate the inherit mode. So I think that makes sense. Okay. That's pretty cool. So let's enforce that it's not shared also. If region is shared, return enval. And yeah, there might be some more things to consider here, but I think we have a pretty decent set of conditions. So let's see if we can build this. Minherit was not declared. I guess we should declare it. Where do they put it? mman.h. Well, I can put it in mman.h too. I very often feel like these APIs are unnecessarily flexible, because in my case, like I would much prefer to not specify a range of memory, but rather like sort of a token of a region in the kernel, because on the kernel side, like if you first mmap like a large chunk of memory and then you say, hey, madvise this little piece in the middle so that it has different characteristics than the whole region I just mapped. That makes things like very complicated for the kernel, because now he has to like split and merge and do all kinds of stuff. And I kind of feel like it would be nice to have APIs that only operate on regions, like entire regions. So once you memory map a region, then the base pointer of that region would sort of be the token that refers to the whole region, and there's no such thing as like partial monmap or partial mprotect or whatever. But it's in POSIX, so just have to deal with it. It's but I think it would be slightly nicer to do things that way. Anyway, let's add the wrapper in the libc, so just like madvise really. Minherit, just forwarding the arguments to the kernel. Let's make sure we get the right syscall number. Okay, clickety clack, and we are off. So let's see. I guess we could put something interesting there to say that we detected that there was a forking. So we'll say that like -1 is the original value. If thread info cache did is -1, oh no, if it's 0, then this is the post fork. Fork detected. Refreshing getted cache. Something like that. Because, yeah. It's good to have a way to detect a fork, because other ways to detect a fork is like cache your PID and then get PID and see if that changes. But then you have the exact same problem again, right? Like then you're doing a heavy syscall, which we don't want to do. We just want to cache this so that it's in our address space and we can just get our thread ID without calling the kernel. Because that is by far the heaviest on that little ray tracer. By far the heaviest user space thing, at least. The kernel's syscall entry looked pretty heavy too. Oh, we forgot to make set inherit mode. Oh, inherit mode. Could have just. Just build faster, Pokey. All right. This will be nice though. Can we accelerate this? I shouldn't have done that. So what's the best way to test this? I guess just start anything and then fork it, right? So we should probably see these pretty easily. Because every malloc will take a lock. So basically every program will malloc, right? Okay, that got screwed. Thread info cache map failed. Did not see that coming. Assert that it's not map failed. So what did I mess up here? I forgot to say private. Is that what I messed up? Probably it is, right? Yeah. I gotta say if you want private or shared memory, dude. But this is a pretty fresh looking solution to this problem, I think. I remember I was sad when I removed the get_to cache originally, but at the same time, it was like, at that time, it was more of a hypothetical problem because I didn't have the profiler to be able to tell me just how much of a problem this is. But now that we see it dominating the profile, we can spend some time fixing that up. So I guess we can just ls here, and we can see fork detected, refreshing get_to cache. That's pretty cool. So let's see if we can test the browser again, maybe. Ray.js. Poof. All right, look at it go. We're in the ones now, dude. In the ones. That's awesome. Okay, well, we had a 1. So let's get a profile of this, because I want to look at this now. So fast. I mean, for perspective, it's like 0.0 something seconds on my host machine, but we're improving, right? So let's see who is taking up the time. Look at that, get_to is completely disappeared, and the syscalls have disappeared as well. So probably that syscall entry function was part of get_to, and we just don't account for it correctly in the profiler. So now that we have eliminated get_to, and now the hash map is once again on top, and we can actually go in here and see instruction by instruction breakdown of what is the hash map actually doing. It's pretty cool. Of course, nothing really stands out. I guess we have a rep mobs here, which is probably what we are doing. But it's all very nice. I wonder if these instructions should be offset somehow. It's like, yeah, I don't know. The lock encode is pretty heavy. So even though we got rid of get_to, we're still doing like an atomic op here, which is still very high in the profile. So the lock stuff in Serenity could definitely use an overhaul. Like it's not very strong. It's very naive and very lacking in many areas. Well, not even taking locks where we should and stuff like that. And the locks are kind of inefficient. So if anybody's interested in that type of stuff, there's plenty of stuff you can improve. But man, that's a really nice improvement. So makes me wonder what is going on more here. Like, can we spot something easily removable? Like optional value. It's kind of interesting that it's so heavy. One thing I like to look at in when you have the instruction sampling in a profile, I like to look at these small functions and then see if you have a lot of samples in the entry and exit of the function, and like not just in the like the function body. Because if you have a lot of samples in the entry and exit, that often means that this function could benefit very much from being inlined. If it's a particularly hot function, because this essentially, if you look here, we have like 10, 13, 14, and 18 samples in the entry and exit. Maybe we don't count this particular one here, but this one belongs to the entry. So we have more, or we have the same number of samples in entry and exit as we do in the function body. So if we inline this, it could potentially get rid of the entry and exit entirely, and it might make it significantly faster. So that's something that we could consider trying out, inlining optional value, because it might give us some serious benefits, because it doesn't look very complex, right? Value. I guess maybe it's the assertion that's the heavy thing. So this is call 70. Right, so it's the assert here that is costing us all the money, because we test the assertion condition, and then if everything is okay, then we just branch to leaving the function. So assertions are a bit annoying, because if you inline assertions, then your code can grow significantly in size if we were to inline this, more aggressively inline this. But at the same time, if you do inline it, you might give the compiler opportunities to realize, wait a minute, this assertion will never fail, because it knows that this has value here is always true in the context where it's inline. So it's hard to know. Anyway, what do we have in clear? What's clear doing? It's kind of interesting. We have many optional or multiple optional things here. So clear has value. So if we have a value, then we call the destructor on the value. So this is a JS value. Wait, I wanted to look at clear. If we have a value, then we get the value. Oh, but because that is out of line, then it doesn't even realize that, like what I was just saying, that in this case, if this would be inlined, then the assertion can be optimized out, because we've already just tested has value anyway. So already clear would probably be simplified significantly by this. Here's another very optional clear. Let's switch to percentage. We're talking 1%-ish of the profile though, so but these guys add up, right? Here's another optional value. It is tempting to try this out. Let's try it out, see what we can do. But first, let's commit what we've been building here. So I guess all of this is the same stuff. Essentially, we get rid of this fork detected thing. Here we go, and we can just do that again. That's fine. It's really cool. I really like this right now, until somebody tells me a way easier way to do this, but for now I like it. So, or actually, let's say we just add let's add everything except getTid change. So kernel plus libc add minherit and map inherit 0. This patch adds the minherit syscall originally invented by OpenBSD. Only the map inherit 0 mode is supported for now. If set on a mmap on an mmap region, that region will be zeroed out on fork. Yes, very cool. And then bring back the getTid cache, I guess, libc. Cache the result of getTid to avoid syscalls. We now use minherit map inherit 0 to create a getTid cache that is automatically invalidated on fork. This is needed since the tid will change if forked. Will be different in a forked child, so we can't have a stale cached tid lying around. This is a gigantic speed up for JS. Pretty nice. For libjs and everyone else too. Yeah, so that's pretty awesome. Now I want to mess with that optional thing. So what if we say that optional value is always inline? So do we have, what is it that you say? GNU always inline, right? We'll do the same here. And we can do the same in value or, and in value without consume state. Okay. And then maybe we can even do clear. So this build will take a moment, but it will be very interesting to see what kind of effects this has. Because I feel like a lot of that stuff was completely unnecessary if you know m has value. And what's a typical location? Like an optional value. That's what we were doing in JavaScript, right? So that's, for instance, what we return when you call getVariable. So when you call getVariable from the interpreter, or from interpreting an identifier, for example, then what we do here is variable, and then we test if it has a value or not, right? So if we're inlining aggressively, then the compiler now knows whether or not this variable optional here has a value. And so if value is inline, it should not need to check that, so the assertion can go away, and everything can go away. And this is the theory anyway. We'll see what it looks like in the end. I guess we can actually look at the assembly right away to see what it turns into. JS, or we should look at it in context. So browser less. Oh wait, it didn't build yet. Now it built. identifier execute. So here we call get variable. And we create an exception and blah, blah, blah. But we don't have, oh, we do have a not call here to optional clear. Why do we have a call to optional clear? I told you to always inline that. But, oh, actually, here's the value as well. Why are you doing that? Why? Do you not respect always inline? Do you not? Or is it the destructor that includes a call? And then because the destructor is not always inline. Why do we get these? Why do we get value like that? Do I have to do this? I can't remember. Like now we're going into cargo cult territory here. I don't remember how to do this. How to say like, no, really inline the thing. So we'll do it to the destructor as well. Where's the destructor? There you are. Has value should definitely be inlined, but we'll say it just in case. Okay, so I guess we'll have to rebuild again a little bit extra here, but we can do only libjs and see what comes out. Or the whole browser maybe. And maybe we'll build a little bit in parallel, please. And maybe not the user land. Okay, I need to spend some time on the build system soon. It's getting a little bit silly again with the hoops you have to jump through to get a build like within a minute, even if you're just doing something small. Alright, so identifier execute. So this got rid of the optional things. Okay, so we have successfully pursued it to not have optional calls. So very cool. Let's see what we get out of that. So I don't know why I wanted to rebuild the userland for some reason. But after that we can sync and see if we gain anything from this optional business. Even if we don't get anything out of it, I'm really happy with the getted cache. That's really awesome. I feel like this happens often if I do performance work, that like I get some big win and then I just want one more win, and like the second win is never as good as the first one. But you get into the zone and you just want to feel that win one more time. So let's get the thing one more time. Clickety clack. 1.89. That's not so bad. So flip it upside down, and I would at the very least expect optional to be gone. And I don't see it anywhere. Be cool to have a way to filter here. It's kind of neat. So identifier execute, we can see here, it's pretty high. Let's switch to percent actually. 2.94% of the profile. But he's doing all of that stuff internally, which is really cool. So what's this rep mobs here? How big is a JS value? How much are we mobsing anyway? We're mobsing three 32-bit words. So this is a 12-byte copy, and I guess that's a JS value. Most likely, yes, it is, because we have the type and then we have a double in here. So that makes him 12 bytes. We could definitely smash it down to 8 bytes by combining information here. I remember that JavaScript core in Safari, they smash values into a 64-bit type, and then they sort of exploit the format of doubles to take some of the unused bits in a double and put type information in there. It's a whole thing, but it's really cool. But I don't think that's necessarily the thing that we want to be doing right now for this engine. That's more like 3 years from now when we're starting to get those types of performance needs. Anyway, this is really quite okay. I wonder if we are consistently below the 2-second mark or what. Clickety 1.7. Ooh, that's not bad at all. 183. Alright, we're just running a couple of runs here. Man, that's really cool. Let's see how long this takes on my machine. Do we have the Ray.js? Click. Yeah, so you can see we're still a bit behind, but we're getting there, one step at a time. And look at that, it's right side up. Colors are a bit off, but we can improve that. Just have to go one day at a time. I wonder if we increase the size a little bit. Now I'm just messing around here, but I'm kind of curious. What if we did like 100 by 100? How long would it take? Still under 10 seconds for 100 by 100. That's awesome. All right, so I feel really good about that get to cache. The optional one feels a little bit like we are overthinking things. What is this? Fly string operator equal to const char star. Basically all of them are here. And interpreter get value. It's this one. Oh, it has to do a character by character compare every time. But since it's using fly string, we could do this. Static fly string. This name is this. And then it becomes a pointer compare, because fly string, if you're not familiar, fly string is it's an interned or sort of deduplicated string class. So any two fly strings that have the same characters inside them are guaranteed to be pointer equal. So you can compare two fly strings, and you know that you only have to do a pointer compare to see if they're the same string. That's the part of the magic of fly string. So if we cache a fly string here with this, it means that we only deduplicate it once, and then this will be a pointer compare rather than a character by character compare. Now it was only 4 characters in that string, right? But still, we're seeing 1.25% of the profile, or 1.13% in that particular compare. So that's pretty heavy, and I think it's okay to do that one. But we really need to improve the hash maps. But I haven't felt like working on hash maps yet. Anyway, I think we're gonna commit some stuff here and then maybe be done for the day. So we'll inline the optional stuff. Inline optional functions more aggressively. This turns into much less code in the most common cases. Here's why. The normal optional usage pattern is something like auto-foo, get me an optional. If foo has value, do stuff with foo dot value. So in this scenario, in this typical scenario, we're checking has value before calling value. Before we check has value before calling value. Without inlining value, we'll double check has value itself and assert if it fails. Inlining allows the compiler to optimize all of this away. So it's a little bit of prose to justify our what looks a little bit like a micro optimization, but I think because of this pattern, which is the common usage pattern that we are now exploiting to generate less code, I think it's worth doing. And then this interpreter change, this one is just for fun. But I mean, variable lookup is really hot, obviously, and the very first thing we do in every variable lookup is compare the variable that you're looking up to string this. So we want that to be fast. And here's optional also, by the way, that exact pattern. So cache a fly string for this to speed up variable lookup. We were hitting strcomp in every variable lookup to see if the lookup was for this. Caching a fly string. This turns that check into a pointer, to one pointer comparison instead. Yeah. Okay. So I think maybe we're going to be done here for the day, but that was a little variety performance work. And as you can see, I'm very, very excited with the profiler that we have here because it allows us to discover interesting things about the programs and allows us to mess around with them and see things that we couldn't see before. So we'll get one more profile here, just close it out, and we'll get this demo thing. Look at all those swirls. Okay, click. And by the way, we can also see into the kernel, and we can even see kernel symbols and everything here. Very, very nice. Of course, if we include the startup of the application, then we see like the kernel doing disk access and stuff like that. So it's kind of interesting. But if we're not interested in like the startup, then we can just skip that by like selecting only this part of the timeline. And we see here that in that particular canvas demo that I just used, we are extremely heavy in blit with alpha. So this is my extremely unoptimized alpha blending code, which is just C++ code that blends colors together. It could be made a lot faster with like vectorization or something like that. And it's something that I keep postponing working on, but we'll see when we get there. Draw a pixel. Look at this. We're touching individual pixels. What's that even about? Draw a pixel. Who calls that? Frame paint event. Oh, shit. Okay. So I guess it's the frame around the HTML view is a GUI frame, and then GUI frame like plots individual pixels, and it ends up taking 2% of the profile. Yep. Room for improvement. And clear rect, what's that doing? Look, it's a rep stas. So clear rect is just like completely, it's like memset for color values, right? We're just memsetting a rectangle with color values. So who is even doing clear rect actually? Clear rect. Oh, I guess it's a fill rect. Wait. I don't like this when some of the stack frames disappear. It's a bit unfortunate, but handle paint event. So I think it's this fill rect right here. So we fill the background color, and then we do we fill the whole widget with background color, and then we paint on top of that. It's very possible that we could optimize this for HTML view and turn off background fill if we haven't already. Set fill. Yeah, we could probably turn off background fill and say that HTML view is responsible for painting himself entirely, instead of relying on the widget system to do it for us. Oh, look at that. Get good random bytes. What are you doing? It's RD rand. Kind of throws me off a little bit that it's always like the instruction after the heavy thing that gets blamed. I wonder if that's so consistent that we should just move this thing. I don't know. Anyway. But yeah, this is the state of the profiler, and we did some cool stuff today with tidcache and a little bit of inlining work for optional. And it seems like if we want Canvas to go fast, then we need to go work on Graphics Painter. Maybe get a better mem copy. I mean, yeah, there might be a better mem copy. Because currently it's like a hand-rolled MMX mem copy, and I think there's probably faster ways to do this. I just didn't look into it too much. Anyways, I'm going to stop looking because I can do this all day and all night. So thanks for hanging out, and I hope you saw something interesting, and I will see you next time.